I think we're all ready to go here, so it's over to you, Bob, to chair the session.
Thanks, Jamie. So I'm glad to share the session now. It's interesting, when I looked at the program of this session, there is actually 7 current or former PhD or MSc students. We start with Cole, who's a current PhD student, jointly of me and Aleks. And this is work with Aleks, and they're talking about the graphical calculus for Lagrangian relations.
Bob, for the introduction. Yeah, so as Bob said, this is joint work with Aleks. So please, if you have a question, then just interrupt me. Oh, shit.
We're having some minor technical problems. Does everything look good online? No?
Yes, it looks good here. Looks good here.
Okay.
So I'm going to give like a brief kind of background and of what the literature is and what we've done in this paper. So John Baez and his students have previously shown how certain classes of electrical circuits can be interpreted in what are called Lagrangian relations. So either linear or affine Lagrangian relations. It's just a minor technical difference. And what these are is a subcategory of linear relations, so relations of matrices. And there's some constraint that corresponds to like mechanical evolution. Yeah, so in this paper on graphical affine algebra by the Talon crew, they also give a graphical interpretation of these electrical circuit components in terms of Lagrangian relations. So this is kind of motivating this talk. So what we'll do in this paper or in this talk is kind of extend this work and give generators for all of Lagrangian relations, not just ones which are interpretations of electrical circuits. And throughout this talk, we'll kind of have 2 kinds of views on Lagrangian relations. So one is over the real numbers. Then this has the semantics in terms of this is semantics for electrical circuits, and then over prime fields, then this is going to be like have a semantics for stabilizer circuits. So this is like quantum versus classical models, depending on which field we use. So yeah, I divide this talk into several sections. The first section is to just talk about like some really basic review of symplectic geometry and Lagrangian relations. And then after this, I'll talk about graphical linear algebra. So this is like string diagrams for relations of matrices. And then in the third section, we'll combine both of these things to get kind of string diagrams for these Lagrangian relations. And then after this, we'll talk about graphical affine algebra. So just this affine extension of graphical linear algebra. And then we'll combine these things again to get graphical affine algebra or graphical affine Lagrangian algebra. Oh, sorry. Okay. So maybe don't mind like the definitions too much, but I've put them up here. So the kind of basic concept, basic building block in symplectic geometry is symplectic vector spaces. So symplectic vector space is a vector space with something called the symplectic form. So it has to be alternating and non-degenerate. And a symplectomorphism is a linear isomorphism which preserves the symplectic form. So in this talk, I'm not going to think about symplectic vector space in this way, but this is like the standard definition. Rather, I'm going to think of it in terms of this lemma. So every finite dimensional symplectic vector space is isomorphic to one with the symplectic form of this form. So that's to say you can split the symplectic vector space into two gradings. So you can kind of see it as like a block with like one thing on top and one thing on the bottom of the same dimension. So there's some kind of physical interpretation of symplectic vector spaces which might be useful for intuition. And the idea is that the vectors in a symplectic vector space are interpreted as like the position and momentum that are allowed, like in a mechanical system. So from this lemma where we split a symplectic vector space into two parts of equal dimension, one part we'll think of as like position and the other part as momentum. So and physicists call this like the phase space of a mechanical system. So the two examples we're going to be working with are like the kind of electrical circuits and stabilizer circuits, quantum circuits. So over the real numbers, or the real numbers where you adjoin an invertible generator freely. This is semantics for electrical circuits. So the grading on the one side is like potential and the other side is current. But over prime fields in the stabilizer setting, the grading is position and momentum observables. So the Z and X observables. Okay, so this intuition I've kind of taken from John Baez's work, and the work of him and his colleagues. So physically, there's these two really important laws for electrical circuits. So the total current of electrical circuit should be equal to the coming in should be equal to the current leaving. So that's Kirchhoff's current law, so otherwise known as the conservation of charge. And Ohm's law says that given a circuit with a current Z and a potential X naught entering and X1 leaving, then the resistance of the circuit can be calculated by taking the difference, the change in potential, and dividing by the current. So in this setting, a resistor with resistance R being a positive real number can be interpreted as a symplectomorphism. So it takes it kind of operates on a state with potential X and current Z, and then it produces a new state with potential R times Z plus X and current Z. So like in this talk, we'll draw resistors as like this kind of squiggly line with the resistance beside it. Yeah. And using these laws, this is we can determine that this is the action of a resistor just by doing algebra. Okay. So the symplectomorphisms can be generalized in a very nice way. So just as there's a notion of the orthogonal complement of a vector space, there's kind of a symplectic version of this, namely the symplectic complement. So the symplectic complement is this this thing here, which we denote by a superscript omega. So it's like all of the symplectic complement of a vector space is the space spanned by the vectors which are orthogonal with respect to the symplectic form, not the standard inner product. What we'll care about is subspaces which are Lagrangian. So that's to say they're equal to their own symplectic complement. So there's various ways to think of the Lagrangian subspaces, which are all equivalent. So I mean, the way I like to think about it is that you have a linear subspace in which all of the rows are orthogonal. So it's spanned by a matrix where all the rows are orthogonal with respect to the symplectic form, and the subspace has maximal dimension, and the maximal dimension is n because of this kind of Galois connection. So every symplectomorphism induces a Lagrangian subspace given by the graph. So this is what I mean when I say Lagrangian subspaces generalize symplectomorphisms. But even more so, you can compose Lagrangian subspaces in a way that's consistent with the composition of symplectomorphisms. So this is kind of the central category of interest in this talk. So the category of Lagrangian relations. So the objects of this prop of Lagrangian relations are symplectic vector spaces with this fixed symplectic form that we had before, where you divide the space into. And a morphism in this category, so from K to N to K to M, is the Lagrangian subspace of the direct sum of both of these symplectic vector spaces. And the composite is given by relational composition. The identity is what you expect. The tensor product, you have to move all of the position to one side and the momentum to the other side, just for bookkeeping. Yeah, like I said, this extends composition of symplectomorphisms. So this is like a proper generalization of symplectomorphisms. Yeah, and this category of Lagrangian relations has been shown previously by Bayes and Fong to be hypergraph categories. So that's to say, every object is equipped with a Frobenius algebra in a way that is compatible with the monoidal structure. So I'll draw these hyperwires induced by the Frobenius algebra as follows. And the interpretation in terms of linear relations, so the interpretation in terms of relations of matrices is given by as follows. So the current on the bottom, all these z's, is forced to be the same by Kirchhoff's law. And Ohm's law means that all of the voltages coming in and the voltage, or the going in and going out, are the sum is the same. So you can kind of do some algebra, and then modulo some trickery, you get that the sum of all of the incoming and outgoing things are the same. And there's a little bit of a trick going on here, because these are interpreted as wires with resistance 0. So you have to do some division by 0. So it's kind of a bit trickery, but it all works out. Yeah, and resistors and these hyperwires interact as they should, as physicists like have like studied in the past. So you have this well-known law where if you take a wire and you split it in two, and then you have two resistors, and then you unsplit it again, you merge them together, then the resistances multiply, and then you divide by their sum. So this is all well known. That's nothing new so far. Yeah, and again, Bayes and Fong they show that you can get more generators here if you work over this extension of the real numbers where you adjoin an invertible element. So the idea here is like when you add this invertible element to T, it's like you're differentiating with respect to time. So you can do you get more generators. So you get capacitors and inductors. So there's a lot of structure which you can express in this setting. Okay, so this is kind of like the background of Lagrangian relations, and I've given some sort of hopefully some motivation of why Lagrangian relations are useful. But now I want to kind of use like this string diagrams more seriously to give more generators and relations for these things. So okay, so there's this well-known presentation of matrices over a ring in terms of a monoidal theory. So given a ring K, then matrices over this ring are presented by these generators and equations. So the white comonoid is like copying and deleting, and then the black thing is like addition and 0, and then every scalar in the ring is like endomorphism on this one wire. So the way to think of this is like by like counting paths. So if you consider a string diagram on the left, and you just evaluate each wire with some with some number. And then if you just follow the action of these things through this path, and you copy them when you see a white thing, and you add them when you see a black thing, then this determines this matrix. So if you have like A, B, C coming in here, then you can just see how this acts on a matrix. So this is the way to think of this. Yeah, and in Fabio Zanazzi's thesis, he went further than this, and he gave a presentation for the prop of linear relations, not just matrices. So linear relations is the category of relations of matrices. So the morphisms are linear subspaces of the product space, and the composition is a relational composition. And so because relations are like categories of spans, then the way to get this is you add all of the generators of matrices, and then you add all the generators of matrices off. And then Zanazzi showed in his thesis that if you just quotient the generators of matrices and matrices off by these additional equations, then this is a presentation for linear relations, so for relations of matrices over field K. And what's really important here is the Frobenius equations. So linear relations actually over a field, there's two Frobenius algebras. So yeah.
Could you explain what's going on with the so A, I guess, represents a number. So
Yeah.
why does it appear sort of upside down as well? What does that mean?
Because the relations is like a category of spans, then you have like a scalar for in the matrices and also in matrices off. So like this guy here is like the scalar A in matrices, and this is the scalar in matrices off. So this is saying that like the opposite of a scalar is its inverse if it's non-zero. So just as this is copying, this is like copying off the transpose of copying. This is a scalar, this is the transpose, because you're considering it in a category of spans. Yeah, and the antipode is like you have this equation that holds that -1 is equal to -1 transpose. So we use this notation that is symmetric for this. Yeah, so because there's these two Frobenius algebras in linear relations, then you can use this notation called like spiders. So if you have a connected a bunch of connected components of one Frobenius algebra, then you can kind of contract them all together, because any two connected components generated by a Frobenius algebra with the same arity are equal. So this is really helpful notation. And maybe this intuition might help someone if they're aware of the ZX calculus, which is something generated by two Frobenius algebras. So in the case when the field is a prime field, then this gives us semantics for the p-dimensional qubit phase-free ZX calculus. So I mean, if you don't know what this is, then later on, John will give a talk related to this, but hopefully this helps some people with intuition. And in terms of Hilbert spaces, this is interpreted as like a generalized Kronecker delta with arbitrary arity. So the white one corresponds to like the standard basis, so it picks out basis elements of the standard basis, and the black one corresponds to the Fourier basis. Okay. So now that we've talked about Lagrangian relations and given this kind of a basic overview of symplectic geometry, and we've talked about this graphical calculus for linear relations, what I want to do is combine these two things together to get some sort of graphical calculus for Lagrangian relations. Okay, so in Pavel's online blog, Graphical Linear Algebra, he made this observation that the color swapping of a functor, so the thing that sends something to its transpose. So you can see it acts on spiders by changing the color, and then it sends scalars to their transpose. This is actually a functor. And moreover, it's not just a functor, it's actually the functor which takes a linear subspace to its orthogonal complement. So using this, we can talk about the symplectic complement of a Lagrangian subspace. So the symplectic complement of a Lagrangian subspace can be reframed here in terms of the orthogonal complement, where you add a -1 and then twist things around. So this is just the translation of what it means for something to be equal to its symplectic complement, i.e. what it means for something to be Lagrangian. So if you kind of uncurry things and do things, consider a Lagrangian relation, not just a Lagrangian subspace, then you get this is the condition for something to be Lagrangian relation. So like the question is, how can we do even more to like get a proper presentation for Lagrangian relations? Okay. So in fact, there's a functor from linear relations to Lagrangian relations given by doubling the linear relation and then taking the orthogonal complement on one of the copies. So as follows. So if you look at this thing on the right, and you can just check that this equation holds. And moreover, so this is like the central theorem of this paper, that any linear Lagrangian relation can be written of the following form, in the following form, for V, a linear relation. So you double, and then what you do is you have to trace out over extra wires and possibly multiply by some elements of the field. So this is kind of like a form in which every Lagrangian relation can be massaged into. And actually, in the case when K is a prime field, then for those who are familiar, not only do things have this form, but all of these A's become the identity. So this is what's known as like the CPM construction. So that's to say that that Lagrangian relations over a finite or over a prime field are CPM of linear relations over the same field. So using this, we can just inductively give generators for Lagrangian relations. So if you look at the image of this doubling functor from linear relations to Lagrangian relations, then all that you have to do to get all Lagrangian relations is add these two extra generators. So it's like it takes the momentum. Oh, so look at this one. This takes the momentum, multiplies it by A, and adds it to the position, and then this is just the one in the other direction. So these two generators, on top of all of the double things, generate all Lagrangian relations. So now we can look at this hypergraph structure of Lagrangian relations in terms of string diagrams. So this hyperwire here that we talked about in terms of electrical circuits, we can now see this Kirchhoff's law just by this doubling. So recall that the things are graded into position and momentum. So all of the gradings on the left are pulled on the left, and all the right are on the right. So the wires on the left sum all the potentials together because this spider here corresponds to the addition monoid. And the one on the right just checks that everything is equal because this corresponds to copying. So this is like a kind of, you can see directly how this corresponds to this Kirchhoff's law that I talked about earlier. And all of the other generators I gave, these have these interpretations. So recall like a resistor, it copies the thing on the right, multiplies it by the resistance, and then adds it to the thing on the left. So this is like at the very beginning, this is just like a kind of graphical way of saying this. And then same with inductors and capacitors. So in this paper on the graphical affine algebra, they have these same interpretations. I don't think they didn't have it in this framework of Lagrangian relations, but they had it in this framework of just pure affine relations. But we can see that all of these things here, these are just variations of this V sub A generator. And there's another equivalent way of looking at the generators. So you can see it as having all of the doubled things as before, and then having this one direction of this, and then having the Fourier transform instead of the other direction. And because you have this decomposition of the Fourier transform, then this is an equivalent set of generators. So this is kind of the more like quantum style generators, like where you consider the Hadamard gate and the phase. So I'll talk about this a bit more later. Okay, so I've talked about graphical Lagrangian algebra, and I've talked about linear algebra, but I've been like alluding to this affine stuff, but I haven't really said much about it. So in this section, I'm going to just kind of go over the work that was done in this paper on graphical affine algebra, just for a quick review. So affine matrices over a field have a graphical calculus, and in particular affine relations over this field have a graphical calculus. So the prop of affine relations has morphisms being affine subspaces of the product space. However, in this setting, affine subspace can be empty. So this is, this is like just the affine version of linear relations, except you can have empty things. And all you need more is these on top of the equations of linear relations. You need to add this new generator, like 1, corresponding to the affine shift, modulo these equations. So this is like, these kinds of Levier theory equations saying that you can copy the affine shift and delete it. And then this one on the left is like saying that if you take the affine shift and produce the empty affine space, then it like collapses all things together by just disconnecting everything and making everything just the topology degenerate. So a way to think about this. So a way to think about this is you can look at so if you just look at the covariant things and not the contravariant things, then an affine matrix can be translated into string diagrams in the syntax as follows. So you do the same thing of counting paths. So you annotate the wires on the bottom going in by A, B, and C, and then you just look at the path, and then here this affine shift, it's like a fixed constant that you for 1. So 1 times y is equal to y, 1 times z is equal to z plus, right, A comes through here. So you can see hopefully how this gives you affineness. And this is nice notation I like to use for this. So if you have if you plug in the affine shift and then some scalar, and then you connect it to this Frobenius algebra induced by addition, then it has this nice property where when you have these two spiders with these so-called phases inside of them, and you connect them together, then you can add the phases. So in particular, this implies that affine relations over a prime field is generated by just these two generators, the copying spider and then the addition spider, labeled by an element of the field in this way. And for those of you who are familiar, this is just like the same as the ZX calculus where you have a NOT gate. So in the qubit case, this is like the p-dimensional qubit shift operator fragment of the ZX calculus, which is a mouthful. But if you're aware of this thing, hopefully this will motivate it. Okay, so now, like just as before, we combined the graphical linear algebra and Lagrangian relations. Now we're going to combine graphical affine algebra and Lagrangian relations to get graphical affine Lagrangian algebra. Okay. So just as the prop of affine relations generalizes linear relations just by adding affine shift. There's a prop of affine Lagrangian relations where the morphisms are just Lagrangian subspaces with affine shift, and everything just works out nicely. And actually, to go from the prop of Lagrangian relations to the prop of affine Lagrangian relations, all we have to do is add one more generator. So that's the generator that, on the one hand, it's the identity, and on the other hand, on the other wire, you add one with this affine shift, and this generates everything. Yeah. So in Bayes and their paper, they use affine Lagrangian relations to characterize a larger class of electrical circuits with voltage and current sources. And in this paper on graphical affine algebra, they put these into pictures. So these aren't exactly the same diagrams, but it can be shown to be, they could be massaged into each other essentially. So you can get voltage and current sources using this this syntax, and this is what it looks like. So this is just, you can just get more things in this electrical circuit interpretation by using affine Lagrangian relations. Okay, so that's the kind of the reason why you'd use affine Lagrangian relations in electrical circuits, but also there's a quantum interpretation. So there's a way to see the Clifford group as being represented projectively by these generators. So this is like the boost operator X. So this is like the kind of the generalization of the NOT gate. And this is like controlled boost operator. So you take a basis element and you do nothing on the first and add it on the second. The Fourier transform, and then this thing called the phase shift gate. And these seen as matrices altogether generate the Clifford group up to scalars. And one says that stabilizer circuits are it's just the subcategory of matrices generated by the Clifford group, as well as vectors in the computational basis and their transposes. In fact, in the odd prime dimensional case, the Clifford group is up to scalars, is isomorphic to the affine symplectomorphisms over the FD to the power of n. And so this is just something to do with symplectomorphisms, affine symplectomorphisms. But in fact, just in the same way that that Lagrangian relations generalize symplectomorphisms, affine Lagrangian relations generalize affine symplectomorphisms. So we can translate these things to each other. So we send this the boost operator. We send the boost operator to this gate here that we added to get affine Lagrangian relations, and then we send this controlled boost operator to this thing, which is doubled. So this is a Lagrangian relation. The Fourier transform to this guy, and then this phase shift thing to this guy, and you can it can be shown that this is this assignment is functorial and isomorphism. And for those with quantum knowledge, the matrices whose rows span the affine Lagrangian subspace are exactly the stabilizer tableaus used in quantum error correction. Yeah, so there's this story of having these Frobenius algebras with like labels associated to them that interact in a certain way. And I said previously that in the linear case, this is the phase-free ZX calculus. In the affine case, this is like this shift operator fragment of the ZX calculus. But in this affine Lagrangian case, in fact, this generates like the stabilizer fragment of the ZX calculus. So instead of just having one label on the black thing indexed by the element of the field, now there's, for every element of the field, you have 2 labels, and they're interpreted as follows. And then you have these fusion rules. So when the spiders are connected, they fuse, and this corresponds to the group, the additive group squared of the field on both spiders. So this is kind of cool because it gives a nice semantics for stabilizer ZX calculus in terms of something that's already known, namely this syntax for affine relations. But because there's this weirdness in the case when the dimension is even, these affine Lagrangian relations over F2, it's actually equivalent to what's called the Backens toy model and not qubit stabilizer circuits. And the reason is because essentially the block sphere, when you kind of truncate it or quantize it into 4 bits in the stabilizer case, but in this setting, because of these rules, you see this is the additive group squared, and you don't have this isomorphism of groups. So there's this kind of weirdness in the qubit case. Okay, so just to go over what we've done here. So at the beginning, we reviewed Lagrangian relations and some basic linear symplectic geometry. And then we also reviewed this work that's been done on graphical linear and graphical affine algebra. And then using these 2 things that exist in the literature, we combine them to get a notion of graphical linear and graphical affine Lagrangian algebra. And importantly, we showed that any Lagrangian relation can be purified in this form. So where you double things and then you trace out the middle. And on the side, we also showed that stabilizer circuits can be represented by affine Lagrangian relations, which wasn't known until now, to my knowledge. So here's some things that we're thinking about doing. So one obvious thing to do, inspired by the kind of quantum side of things, is to work out the measurement in the affine Lagrangian relations. So I'm pretty sure that if you look at the CPM construction, so you're adding the quantum discarding to Lagrangian relations, and this would give you coisotropic relations. And then you can split the idempotent corresponding to decoherence in this category to have like a conditional, to have like classical measurement. So I know Guillaume is giving a talk tomorrow, I think, on a similar topic. So if you're interested in this, then you should watch this talk. Yeah, and one other thing to do is we kind of bootstrap this monoidal theory for affine relations by doubling, but we don't really have like a proper completeness result in this case because we're just kind of appealing to this doubling thing and looking at the, like we don't have the rules we have don't preserve being Lagrangian. So the question is there a way to like to characterize Lagrangian relations in terms of generators and equations that in the proper way? And the proof of this would probably just be like the completeness proof of the stabilizer ZX calculus, which would involve looking at graph states and local complementation. And then there's also a kind of technicality which we just decided not to do, namely that there's a way to define Lagrangian subspace in terms of not over just a field but over any PID. So it's probably possible that all of this stuff holds when K is a PID. And then finally, this whole time I've been going back and forth between this interpretation of electrical circuits and this interpretation of stabilizer quantum circuits. So I think this kind of begs the question of like, is there a deeper connection between the electrical circuits and the kind of quantum circuits? Because I think this connection is kind of to this point unexplored.
Okay, thanks, Cole. Very nice. Very nice. Does anybody have a question?
A question from John and Wetering.
Cool, thanks for the talk. I was wondering, because you give this example of electrical circuits, and it's kind of because you have these two complementary variables like voltage and the other thing. And I was wondering, because if you also just look at momentum and position, because there's also two complementary position, can you get like a graphical calculus for classical mechanics? Like, can you write down a Hamiltonian and have some sort of like discrete time evolution of a state? Does that make sense?
Yeah, I mean, in this paper by Baez and his students, they do a similar thing, but the restriction is that it all has to be linear, obviously. So, but any like linear.
What does it mean in this context to be linear? Like in terms of
linear, like you have vector spaces and linear transformations, not like manifolds, like which is like where like a lot of interesting physics is going on. But yeah, this is just like a generic thing about symplectic geometry.
Okay.
Okay, any more questions?
I have a question. So you talked about this nice purification result, and I think my understanding of the talk is you might be able to use this to give a semantics for electrical diagrams. And then in the semantics, because you have all this nice Frobenius structure, you can simplify down sort of the meaning of the circuit that you want to get. So my question is, would you be able to sort of go backwards and use this as like a circuit simulation technique? Because I think people do this for quantum things, but I've not heard of anyone doing this for like electrical circuits or anything like that.
I mean, I guess it's possible to do, but I think this is not like a problem that is very difficult to begin with. So unlike in quantum circuits, like the reason people want to simulate them is because it's like so intractable that they're using all these heuristic techniques. But I think like as far as like electrical circuits go, physicists probably are happy just like, you know, solving differential equations. And I mean, I don't maybe it's useful, but it's not like as
well, it would save like if you imagine a lot of electronics are mass produced and stuff, and they might have many repetitions of the same sort of thing going on inside, and it's all designed modularly. But if you were able to sort of simplify it down and then get the computers to tell you what the most efficient by number of parts circuit, that would have non-negligible economic impact, I think.
Yeah.
We should keep this discussion because we're kind of running out of time. And Robin just said that a lot of this will be in Yeung's talk tomorrow. So, right, so we can continue in the chat this discussion because it's going on now. So let's move to the next speaker. So who's going to give the talk? Yeah.
Yeah.
Oh, clapping. Sorry.
You still turn off just so it doesn't.
Okay. So John, you're doing the talk, okay?
How does this? Oh, scroll. Jesus. Okay. Ah. Okay.
Yeah.
Okay. Sure. Can I?
Okay. So the following talk continues the theme of graphical quantum-like languages. It's about the edge calculus, completeness and extensions by Miriam, Aleks, Hector, John, and Sal.
Okay, thank you, Bob. Yeah, so this is joint work with Miriam, Aleks, Hector, and Sal. And you stand here. Okay. So this is talking about the ZH calculus, which is a graphical language for reasoning about quantum computation. Okay, great. So this is about the graphical language for quantum computing, for qubit quantum computing. And actually, I put the abstract of our paper into this website where I generate a title based on the abstract. And it told me that it's about the ZH calculus, an alternative GUI for quantum information. I think this is a good description. So the graphical user interface, we're talking about quantum computing, really. And it's an alternative GUI because it's not the ZX calculus, it's a ZH calculus. Okay, so why is this not working? So the ZX calculus, which some of you might be familiar with, is a universal and complete language for quantum computing. So you can do anything graphically that you want to reason about quantum circuits and stuff. And this is a great language if your gate set is like Clifford-less phases, which is a very common gate set for quantum computing, but it's not the only gate set. And for instance, if we think about Toffoli gates, which are these like controlled AND gates, which are also really useful, then ZX calculus, the reasoning is like harder, like it's less natural to reason about those things. And so the ZH calculus was introduced to be like useful for these Toffoli gates, for these multilinear logic gates. The original ZH calculus was introduced in QPL 2018, and it was shown that this was a complete language for the universal fragment. So universal here means where we have all the unitaries on qubits. Yeah, and what we did in this work is we actually showed that a subset of those rules is already complete for the Toffoli-Hadamard gate set. So Toffoli-Hadamard gate set is a very small gate set that is already enough to approximate any quantum computation. So you can still do everything with a quantum computer that you want to do, you can do with just a Toffoli and Hadamard gate. And then we also find that actually if you take this original set of rules, that you get a universal calculus over any ring. So not just the complex numbers, but pretty much any ring. Okay. Yeah, and also along the way, you found a nice way to encode arithmetic in ZH, which I'll get to. Okay, so motivation for this ZH calculus and why we do these things. So if we have just a Boolean map, so a map of bit strings, then this generates a linear map on the tensor products of C2, of the two-dimensional complex vector space, just by its action on the computational basis there, so just on like a chosen basis. For instance, this is like sort of introducing the notation that I'll be using. So we have the NOT gate, which is like this gray dot with like this negation symbol. We have a copy gate, which I write as the spider, which like my diagrams are going up. So there's like a single input and multiple outputs. And then we have the XOR, which is the gray spider, multiple input, single output. And then ZH is really asking, so these things already occur in ZX. And ZH is really asking, okay, what about the AND gate? Like what do we do with the AND gate? Okay, so copy, XOR, and AND are all symmetric with respect to swaps on inputs and outputs. So we can interchange all the inputs and like, or like the outputs in the case of the copy, and it remains the same thing. But the special thing about copy and XOR is that they also have this property called flex symmetry, which is a term coined by Bertrand, which is that if I use my compact closed structure, so my cups and caps, and I interchange an input and an output, I also still have the same thing. So these are sort of like extra symmetric. And it turns out that this is not true for the AND gate. So for the AND gate, we cannot like swap an input and output. Okay. And so, yeah. So the starting point is can we make the AND gate flex symmetric somehow? Can we get like a related thing that does have this extra special symmetry? And it turns out that yes, there is a linear map, which I write as a small square, which if I apply it after the AND gate, it does have this extra symmetry. So that's really nice. And it turns out that this AND gate is this special map is the Hadamard gate from quantum computing. This is a very common quantum gate. It's kind of like the single qubit Fourier transform. And then using this, we can define this sort of new thing, which we call an H box, named a Hadamard box, which is the sort of the flex symmetric version of the AND gate. Okay. Okay, so that's sort of the motivation behind our generators, because we have two types of generators in ZH calculus. We have the Z spider, which, if you're familiar with ZX calculus, it's just the same thing. It's kind of this generalized Kronecker delta, so like it matches, it checks whether all the inputs are the same, and then it outputs the same on all the outputs. And then we have the H box, which is the thing I just described. And like as a matrix or as a tensor, it has like ones everywhere, except in the bottom right corner where there's a single -1. Okay, and so this is like fully symmetric in this way. And then we have some additional generators, which is sort of for bookkeeping. So we have this star, which is just a scalar, just a half, and it's useful to have around for the calculations. And we have a standard complex code structure. So we have an identity wire, a cup, and a cap. We also have a swap, which we didn't do. Okay. And it turns out that these generators are universal over any 2 to the n by 2 to the m matrix, where the entries are in this ring Z over a half. So if you have dyadic rationals, you can represent it using just these generators. And this is resolved by Amy et al., which says that these matrices precisely correspond to those you can generate with a quantum circuit which consists of Toffoli gates and an even number of Hadamard gates. The even number comes from the fact that the Hadamard gate actually contains a 1 over square root of 2, and we only have a half, so we need 2 of them to get a half. But that's really just a technical issue. So okay, so this is a universal language for Toffoli Hadamard circuits, essentially. So now let's see what we can actually do with it. And for that, I'm going to sort of reintroduce these generators we've already seen. So we can just define these gray spiders using the generators I've just shown. So for instance, the gray spider on the left is just a Z spider, where you put Hadamards everywhere, and we do some rescaling, so renormalization. And the same thing with like a knot on the top, so we get sort of a generalized knot gate. And also we get this Z spider with a knot symbol, which is like a kind of a Z gate in quantum computing. And we have this interpretation in Boolean maps. So then we have a NOT gate, copy gate, XOR, and AND. And then we can write all our rewrite rules we want in terms of this Boolean interpretation. So, for instance, the copy gate is sort of like co-associative. This is the first rule on the top, and this translates to the spider fusion rule. So we can fuse spiders together. And the same thing, the AND gate is associative. So we get this sort of H-box fusion rule. But now we have to like have an additional Hadamard in the middle, but then these things fuse together. Copy, well, if you have a single input, a single output, well, that does nothing. It's just an identity. So we can also remove an identity. And the AND gate, a single input, single output, that also doesn't do anything because it just checks the AND on like a single bit. So it's also an identity. So from that, we get the 2 Hadamards in a row gives an identity. Second set of rules is a little bit more complicated. There's 2 bialgebra rules. So if we have an XOR and then we copy the output, it's the same thing as we copy first all the inputs and we sort of like give them to the XORs in the right way, and the calculus is the same thing. So we get from this sort of the standard bialgebra rule that you also have in ZX calculus. But we also have a bialgebra rule coming from AND and copy in exactly the same way. And this gives a way for the gray spider and the Hadamard, the gray spider and the H-box to interact. And then we also have this rule with 2 knots is of course the identity. And this is equivalent to this thing I wrote on the right, which like you have to do some calculations, but using the other rewrite rules, you can show this is sort of equivalent. We need one final rule, which is a bit more complicated. And what this says is, if I take an input and I give it to an AND gate and I negate it and give it to another AND gate, then one of these AND gates, the output will be 0 because I'm giving a 1 and a 0 to one of them. So the only way the outputs can be equal is if the outputs are both 0. Okay, so this is kind of a property of the AND gate. And this translates to this rewrite rule on the right. So this is a bit more complicated. And because it's a bit more complicated, luckily we have a pair of simple rewrite rules that are sort of equivalent to it. So if we have these latter 2 rules, we can prove this above rule. And if you have the above rule in combination with all the other ones are shown, you get the other 2 at the bottom. The other 2 at the bottom really says that, well, the only way an AND gate can give 1 is if both my inputs are 1. That's the first rule. And the second says if I copy an input and I give it to an AND gate, well, it's the same thing as doing nothing with my input. Okay. So we have these 8 rules for the ZH calculus. So we have the spider fusion rule, H-box fusion, we have 2 identity rules, we have 2 bialgebra rules, and then we have these 2 things which are more specific to our calculus, this M and O rule. And it turns out that these 8 rules are complete for matrices over Z half, so over dyadic rationals. And the way we prove this is we show that each diagram can be reduced to a unique normal form, and this is like the majority of our paper, which this takes about like 40 pages to prove. And this is really nice because this means that because this is a approximately universal gate set or a set of matrices for quantum computing. So essentially all of quantum computing boils down to these 8 rules. Like in principle, you could do all quantum computing using just these 8 rules, which I think is quite surprising because these are not that many rules. Okay. So that's like the first part of the paper, which is about sort of the phase-free ZH calculus, where we have no parameters. But a thing that you find when doing the proof is that you find some structure that's really useful. And we call these things labeled H-boxes. So I'm going to talk about those next. So when we have a state, which is like a vector with like a 1 in the top corner and an A in the bottom, where A is some number. We represent this using like a special kind of derived notation. So for instance, for -1, this is just a standard H box. But also for 0, we get a gray spider, and for 1, we get a white spider. And we can extend this to not just single output states, but also to multi-output states, just by this like definition. And we can build higher numbers using this sort of successor construction. So there's like multiple ways to write this here. But yeah, you can, if you have an H box, like a labeled H box for a number A, you can build one for A plus 1. And that means we can build all natural numbers just by starting with the 0 and then just like successors. And we also get negation because we can do this like Z gate after it. And so we get all the integers. We get all the integer labeled H boxes. This is kind of a way to start encoding piano arithmetic in our calculus. And we have a couple of like little diagrammatic gadgets that allow us to do these operations. So this thing gives us addition. And proving this is that this is correct is one of the big things we do in the paper. We have multiplication, it's also really simple. We have this thing which might seem a bit arbitrary, but it's actually really useful in the context of a proof, which is that you can sort of average two values. So the thing on the right is kind of like multiplying by this like not 2, which is kind of multiplying by a half. So this is sort of like an average rule because you get an outcome that's kind of like A plus B over 2. And we get a final thing which we call the introduction rule, because it allows us to introduce additional wires to an H box. And this is also just a really useful kind of calculation. The reason I'm showing you these things is because we can lift these labeled H boxes, which in this setting are just like a convenient syntactic sugar, but we can lift them to actual generators in a more general setting. Okay. So yeah, so we can think about not just matrices over the dyadic rationals, but over more arbitrary rings. And then we need to have these as actual generators. So we pick a commutative ring R, where the 2 elements, this is like 1 plus 1, has an inverse half. And then we define these labeled H boxes now as actual generators of our calculus. So it's the same definition, but instead of like a -1, we have like an R there. So this is a matrix where there's ones everywhere, but there's an R in the bottom right corner. And then we get some resulting diagrams that we call ZHR diagrams, and these are universal for matrices over this ring R. So you can represent any 2 to the n by 2 to the n matrix over this chosen ring. And we also get completeness, but for that we need a couple more rewrite rules. So the first 6 rules you see on the top 2 rows are essentially the same as I've shown before, except that the H box fusion rule, on like on the left side, you can now fuse H boxes which also have a label in there. And we see on the bottom rows, they are these things which we were like sort of proven in our phase 3 calculus, and now we assume as axioms. So we have this multiplication rule, we have this average rule, introduction, and this relation of the one element, the unit element, to the Z spider. So we promote these things we could prove in our like simpler setting, and now we make them axioms. And this is complete for matrices over R. So if you have any ring which is commutative and where 2 is an inverse, this rule set is complete. Okay, but we can actually do something slightly more general, because not all rings have an inverse for 2. For instance, if you want to take our ring to be the integers, this is a problem because one of our generators was this star element, and the interpretation of this element is to be a half. So we don't have access to this star, so we need to get around that somehow. And the way we get around that is, instead of defining our gray spiders as like derived generators, we promote them to be actual generators. Okay. And then the definitions of the gray spiders we had before now become axioms, but they sort of become scaled up. So instead of having like a normalization of a half on one side, you put a normalization of 2 on the other side. So we add these 2 new rules. And we need a new meta rule. So it's not really a diagrammatic equality, but more a sort of additional type of reasoning we have to add to our calculus, which is that if we have a diagrammatic equality where there's like a scalar 2 on both sides, so there's like no input Z spider, no input, no output Z spider, then we can cancel this. We can cancel this spider. And this like meta rule is only sound when 2 is not a 0 divisor in your ring, because obviously like you can't cancel it. Okay. So what we then get is if R is a commutative ring where 2 is not a zero divisor, then the rules I've just shown plus the meta rule makes R complete matrices over R. Okay, that's what I want to say. So to conclude, we found a new small and complete axiomatization for Toffoli-Hadamard circuit, which is an approximately universal gate set for conflict revealing. There's a clear relation to sort of identities of Boolean circuits. And we can straightforwardly extend this rule set to work for almost arbitrary commutative rings. Thank you for your attention.
Thank you, John. Are there any questions? If not, I mean, oh, is there one?
Yeah.
Okay.
Yeah, thanks for the talk. So your axiomatization, you had these 8 rules. I'm just wondering, are they minimal or could you potentially get a smaller set of rules?
It's a very good question. We tried very hard to prove they're minimal. You also have to ask us, some of these rules, the way you've written them are sort of infinite families of rules, like the spider fusion. And you can decompose these into like a set of finite rules if you view hierarchy spiders as sort of derived generators, you get a finitary representation. If you have a finitary representation, you can ask, okay, is this minimal? And you can show for quite a few rules that they are necessary, but there's still quite a few where it's really hard to do. In particular, the bi-algebra rule. So the bi-algebra rule with 2 inputs, 2 outputs. Like this is always like the crux, because you like it sort of feels like you change connectivity of the graph. So it feels like you should be able to prove that this is always necessary because you need to change the connectivity somehow. But like we haven't succeeded in proving this, and there's also a problem with ZX. Like also the reason why there's also the thing where it's not known if this is actually necessary.
So even for ZX, you don't know if the bi-algebra rule is necessary?
No. It's just, yeah, you need to find some kind of invariant that's preserved for all the variables except the one you're trying to prove necessariness of. And that's just, we haven't been able to succeed for bi-algebra with that. So yeah, we don't know if it's minimal, but I would be surprised if this wasn't minimal, because this is already a really small set of things.
I mean, I wouldn't even be, if a surprise is an understatement, the world would collapse, I think. So any more questions? In that case, I got a question just to see that I understand what you're saying, John. Can you go to the previous set, like the one without numbers?
This one?
Yeah, so do I understand it well that your statement to compare this with the X is that here you get an approximate universal or whatever you call calculus without any variables? Well, you can do the same with the X, even with 5 rules or something like that, but then you've got the need of variables. That's the main difference, right?
So there's of course Clifford ZX, which has a very small axiomatization, but that's not universal. You have the universal axiommatizations, but they all have this sort of like uncountably infinite axiom schema, because you need to relate somehow like the block structure. I think the closest you can get is Van Novelmar's calculus for the ZX triangle, which is closely related to this rule set, but he needs more rules. But it's sort of the same set of matrices he gets. Yeah, I guess Clifford plus T also has an axiomatization that is finitary, like you only need a finite set of rules, but the rules are more complicated, you need more of them.
Yeah, so and you need variables in it. I think that's the key difference, right?
I mean, like variables, like you can just, if you only have pi over 4, like you say, okay, pi over 4 is just a generator, pi over 2 is just a generator, like it's, yeah.
Okay, thank you, John. Nice, very nice. We clap. Do we clap? Somebody has to open. Okay, we clap. Is it open? No. Sorry, John, you don't get a clap. Well, you got mine.
We clapped in Yearbow.
Huh?
We clapped in Cambridge.
Oh, you clapped in Cambridge. Okay, good. So we go over to the next talk. So Richie or Alexis, who's going to do this? Richie.
Hello, can you hear me?
Yes, I can hear
Can
you.
you? Okay, good. Can you see? Do you see my screen?
I can see
Is
your
it-
screen. Yeah.
Is
I
it
can
big
see-
enough? Is it big enough in Cambridge and so on?
I mean, it's perfect. But
Yeah,
I've
okay,
very big
okay.
screen, you know that. So it's
Okay,
never.
cool.
Okay. The next talk is given by
Sorry,
Alexis.
it's a little small if you want to be able to read it, I think.
Is this better?
Yeah, that's much
Or
better. Thank you.
Is this enough? Yeah. Okay.
Okay, so the next talk is given by Alexis, Richie, and Giovanni, who are all in some way connected to Cambridge Quantum, and they're going to talk about diagrammatic differentiation.
Yeah. Thanks, Bob. So yeah, today, as Bob said, I'm going to talk about diagrammatic differentiation for quantum machine learning. Yeah. So this joint work with Alexis Toumi and Giovanni de Felice. So yeah, let's get started. Big theme of ACT is compositionality. Well, in my opinion, derivatives are a compositional thing. At school, you first learn the derivatives of elementary functions, and then you learn rules on how to differentiate functions that are composed of these elementary functions. So similar to that, since diagrams are made of smaller boxes that are composed together, what we did is we show how to differentiate diagrams using the derivatives of the smaller boxes. Specifically, we transfer this to ZX diagrams and then classical quantum circuits. And we took all this theory and we implemented it into DiscoPy, which is a Python library for representing and manipulating monodal categories. An overview of the talk, I'm going to first introduce some basic mathematical concepts such as derivations and dual numbers, which are used to formalize regular differentiation. And then I'm going to extend these dual numbers to monodal categories to get dual diagrams, which are used to formalize diagrammatic differentiation. Then, like I said, we're going to talk about differentiating ZX diagrams, and then we're going to talk about differentiating classical quantum circuits in the form of mixed ZX diagrams. Okay. Yep, so here's some code. I might end up repeating myself more than once just because, there's the code version and the theory version, but here we go. So here you have a monodal diagram in DiscoPy, which represents a circuit. Each box here is defined as these matrices. Since f and g are parameterized by the variable x, we need to give the derivatives here as a dictionary. And we build the overall diagram like this. First, we take f, we tensor it with h, and then we compose it with g to get a diagram like this. Now, like I said, the main topic of this talk is to think about whether there's an algorithmic way of taking this diagram and then differentiating it using the derivatives of the individual boxes. Okay, so yep, let's define a few things. Start with commutative rig. A rig is a set S with two commutative monoids, addition and multiplication, such that the multiplication distributes into the addition. And the reason we talk about commutative rigs is that rigs are the minimum structure we need to define matrix multiplication. And it's also the minimum that we need to talk about dual numbers and derivations. And now onto the definition of a derivation. Given a commutative rig S, a derivation from S to S is defined as any operation that satisfies these linearity and product rules. If you know differentiation, this should be quite familiar to you. So obviously differentiation falls under, is considered derivation. And yeah, so a related concept to derivations is that of dual numbers. And dual numbers are first introduced by Clifford. And the way dual numbers are defined is sort of similar to, there's two intuitions to this. So first one is that it's similar to the complex numbers in the way it's defined, in that in the complex numbers, you take the reals, you introduce a special element, I, such that I squared is equal to -1. And then here, instead of using the reals, we take a rig, S, and then we introduce a special element epsilon, such that epsilon squared is equal to 0. So the other intuition to this is epsilon is a small number, so epsilon squared is extra small, so we ignore terms that are beyond second order. And to define the sum and product of dual numbers of the form a plus b epsilon, you simply just add them together component-wise, and you multiply them using the commutation and distribution rule properties of a rig. So if you look at these two equations, if you look on the right-hand side, you notice that the real component corresponds to the operation that you perform in the original rig S. And if you look at the epsilon component, you'll notice that, in fact, that it's the derivation of that element in S. So the derivation of a times b is a times b prime plus a prime times b. And in fact, there's a one-to-one correspondence between the dual numbers and the derivations. So that's how they're connected. If you take a derivation, you can define a rig homomorphism, which corresponds to a dual number construction, by mapping each f in S into f plus delta f. On the other hand, you can take any rig homomorphism, and then you can apply it and then project it on the epsilon component to get the derivation like this. So since dual numbers and derivations have a one-to-one correspondence, to differentiate, you just need to pick the right dual number system and then operate from there. An example of this is the rig of smooth functions. If you have a smooth function f from R to R, you can lift this function to the dual numbers by using this equation, which is derived by essentially Taylor expanding f at A and then discarding the epsilon squared components. Yeah, using this equation and the previous properties of a rig, you can combine them and derive the linearity, products, and chain rules that we're very familiar with. And the intuition here is that, yes, so to actually perform automatic differentiation on f at A, all you need to do is evaluate fa plus epsilon using, say, this rule and the dual number rules, and then projecting the epsilon components. We'll see this a bit more later on when we extend it to diagrams, and then I show how it's done in the scope line. So yeah, let's transfer what we know here from dual numbers to dual diagrams. How do we do this? Well, we need to take a monodal category and then enrich it in commutative monoids. So the way to enrich it in commutative monoids is that for each Hom set, so for each input-output type pair, you need to come up with a monoid where, well, a monoid has an addition operator and there's a zero element, such that if you have two elements of the same input-output types, you can add them together to get another diagram of the same input-output type. So that's what's going on here. So if you do like the box F plus the box H, you get an overall diagram with input types and output types of 1 qubit and 1 qubit respectively. And obviously the zero has to act as the element in the monoid. Yeah. Oh, and then for this diagram, it's just to exemplify that the composition and the tensor operators distribute over the sum. So if you do F plus H as you have here, and then you tensor F, well, you need to tensor both of them by F. And then when you compose by G, you need to compose both of them by G. So now this is what it looks like in DiscoPy. Now that we're enriched our monodal category with commutative monoids, we need to introduce the scalar box like we did in dual numbers. So we introduced the scalar box such that epsilon squared is equal to 0. And we map this category C to the dual of C by functorially mapping each box from F to F plus delta, like we did for dual numbers. So what does this look like in code? Well, first I need to introduce this box. This array them, this value doesn't mean much. We just bring it there. And now to define a function in DiscoPy, you need to define a mapping on the arrows in particular. And the way we do this is, well, if the box doesn't contain any parameters, we just return the box itself. But if X is in that parameter, and X is a parameter of that box, then we need to look up the derivative and construct the derivative box. And then you do you return box plus the derivative box tensor by epsilon. Okay. So if you do all of this, you get a functor, and then you apply it to your diagram, and you will get something like this with 4 terms. And as before, the real components gives you the original diagram. And if you look at the right-hand side term, it contains 2 epsilons, so that equals to 0. We need to remove that later. But if you look at the 2 middle terms, that corresponds to the derivation. Now, what I need to do to get derivation is just select all the terms such that epsilon appears exactly once, and then I remove the epsilon itself, and then I return those terms. So if I do all of this, what I get overall is, well, you start from this diagram, and then you differentiate to get this derivation. This is what the matrix looks like when you actually compose it together explicitly. And as a sanity check, when you evaluate this diagram in the DiscoPy, you're going to get this matrix, which, you know, if you check, means it's correct. Phew, okay. In practice, we don't want to actually evaluate our diagrams, differentiate them like this, and by hand you wouldn't want to do that either. So there's in fact some nice, I think, diagrammatic calculi for differentiating diagrams. All you need to do is introduce this thing called bubbles. So why do we need these bubbles? Well, you kind of want to say it's a functor, but if you don't think about the dual numbers and you don't think about the projections, if you just apply the operation on the diagram, you wouldn't you wouldn't get it's not functorial. So you need to instead use a bubble, which is just a unary operator on Hom sets. So when you apply a bubble on the diagram, you get the bubble wrapped around the diagram. And what the calculator looks like in practice is that you have to apply the Leibniz product rule on both the composition and the tensor product. And it looks like this. So if G is unparameterized, then the derivative of G is 0. So that means these 2 terms are 0. So if you just look at these terms here, it looks as if the bubble can pass through the unparameterized part of the diagram. So if you use this in practice on, say, ZX diagrams, it's very intuitive to use. So now on to differentiating ZX diagrams. To differentiate ZX diagrams, since ZX diagrams are freely generated by some generators, we need to give the derivatives of its generators. So the generators are the spiders, the Hadamard, the cup, and the cap, and the swap. Most of these are unparameterized, and if you want to differentiate the unparameterized boxes, they equal to 0. So excuse me. Okay, I'm back. So to differentiate the unparameterized boxes, since they equal to 0, you don't need to do anything there. They just become the empty diagram, like we said before. To differentiate the parameterized diagram, parts of the diagrams, for example, the spiders, you need to give special rules for it. Thankfully, it turns out you can bootstrap these rules by first giving the rule for a single spider, one-legged spider, and you can check this algebraically using vectors. And then you can extend this to extend this to multi-legged spiders by diagrammatic rearrangement. So you can see here, you can rearrange it, and then since this part is unparameterized, you can push the bubble through, and you multiply by a scalar, and then you do some fusion, and you'll get back this. So the overall rule is whenever you see a spider, you can just add pi and then multiply by a scalar. Okay, so there's a little bit of a catch. So if alpha is not just the variable you're interested in, but a function of the variable you're interested in, you need to be able to express the derivative as a ZX diagram. And if the derivative is unbounded, then you're not able to express it as a ZX diagram. Yep. Okay. So this is how you would differentiate. This is how you differentiate ZX diagram in DiscoPy. You define or a circuit like this, you apply circuit functor to Zx, and then you will get something like this. The 0.5 corresponds to a pi because of scaling in this pi. It's from 0 to 1 instead of from 0 to 2 pi. So now let's move on to circuits. To differentiate a circuit, or a circuit is in fact a double diagram by the CPM construction with a line of symmetry in between, and the reflection represents diagrammatic conjugation. However, in general, we have the problem that derivative of a double is not equal to the double of a derivative. So the problem with that is when you differentiate a circuit, since if it appears once in the original circuit, when you double it, it will appear twice. You need to apply the product rule. And when you apply the product rule, you get a symmetry. And the symmetry means you can't evaluate this on a quantum hardware since it's no longer like a double diagram. So what we really need is a way to differentiate double diagrams, a double generator back into double diagrams. So to do this, we can use the parameter shift rule. So it turns out when you differentiate the Z rotation, you're able to express it in terms of linear combination of the Z rotation, which means you don't even need to change the topology of your overall circuit. You just need to change the evaluation points. And yeah, so because we can differentiate the RZ gate, like similarly to the ZX, vanilla ZX version, you can use this to derive all the other rules for the other gates, since it's the only parameterized generator you need. Yep. You also need a -1 scalar. So if your version of ZX doesn't have the -1, you'll have some. Okay, so yep, this is what it looks like. This is what a circuit looks like in Disco Pi. The only parameterized gate here is RZ, and when you differentiate it with respect to phi, you'll get a linear combination of two circuits. And both of these can be evaluated in the hardware. So with some post-processing, you can differentiate that circuit. If the Z appears more than once, then you'll get, it appears twice, you get 4 terms by, the product. Oh yeah, so to do post-processing, you can use these bubbles again. So previously we used bubbles to differentiate diagrams, but here you can actually think of bubbles as post-processing. In particular, I know it's not very clear, but the sigma represents an activation function. And to differentiate through the bubble, you need to do this, which represents, NM-wise multiplication. So with all this in mind, we're able to kind of take some other people's work on quantum machine learning, and we can express it directly in diagrammatic notation. And just with that, we're able to, we're providing semantics on how to differentiate these diagrams, these experiments. So in this paper, they did some supervised learning on a quantum machine. It's expressed like this. So this part is a doubled circuit. So this would actually be evaluated on quantum hardware. And this undoubled singles part of the circuit is evaluated on classical hardware. Cool. Okay, so I have a couple of minutes left. I'm going to talk about Stone's theorem. So what Stone's theorem...
You got 1 minute left, Richie.
Oh, okay, I'm gonna try to get through this. So Stone's theorem says if you have the Hamiltonian that have the Hermitian, you can get the unitary group. And it turns out, given a phase gadget, which is a unitary group, you can differentiate it and get the Hamiltonian. And if you have the Hamiltonian, there's a correspondence between the things. Long story short, this in fact we're actually solving sort of a differential equation, and it's kind of neat. So that could be a direction we can go towards. So future work would be to find the exponent of a Hermitian diagram. So we're taking calculus and turn it into like solving a combinatorial problem. Yep. Okay. So that's pretty much it from me. So if you want to check out this a bit more in practice, you can go on Disco Pi and read the docs.
Thank you, Richie. Are there any questions?
Yeah.
Is anybody moving there?
Oh, we muted, yeah.
Am I getting a question from Cambridge?
Yes, one question here.
Yeah, okay.
Thanks,
Hello.
Richie, for the thanks, Richie, for the talk. Is there an
Hi.
equivalent, or is there a notion of diagrammatic integration? And do you get, if so, do you get a constant of integration term? What does that look like? Like, say, to do integration by parts.
That's a good question. So I think sometimes, so I think someone has tried doing integration of diagrams. So I think Chen et al. They had some restricted rule on integrating certain types of ZX diagrams. I'm not sure it works in general. I think I was at a ZX talk, and when they presented it, someone might have even said there's maybe like a no-go theorem for this, but certainly there's definitely rules for integrating certain diagrams, which is sort of what I'm hinting at here. We might turn integration into like a combinatorial problem rather than, just a magic trick. When you integrate stuff, there's really no clear way of doing it. But if you phrase it as a combinatorial problem, maybe there's a way.
Thank you.
Robin, you got a question?
Yep, can you hear me?
Yeah.
Thanks for the talk. Yeah, I just had a quick question about the sums that you use, because it seems like a lot of the semantics you have in mind have a sum on Hom set that is representable internally as a sum operation itself. Yeah. Could you use this instead of just these explicit sums? I know it was a big deal for ZX to get rid of the explicit sums like that, or is there just some obstacle I'm missing?
Oh, so you're asking, is it possible, say like here, like if you have multiple parameters, you get a sum of diagrams. Are you saying, is it possible to go directly from diagram to diagram without sum of diagrams?
Yeah, to represent diagrammatically the sum,
yeah,
some internal sum operation like you would have on, I guess you might have
so
that, but you have that also for functions, from the reals to the reals or whatever you're differentiating.
Yeah. This is something I've actually thought about a little bit. So and I spoke to Hani about this, and he said, yeah, this is an important thing. We probably in the future you want to be able to go from a derivative of ZX diagram to another ZX diagram without going to the sums. I haven't thought too much about it. I have thought. Okay, I have thought a bit about it. I don't know how to combine the diagrams directly. It might take a little bit of work, but I feel like it's possible. In the circuits case, I know for a fact that sometimes you need at least two terms, just because one term is not enough, because it's not a double diagram, so you can't express it as a single double diagram. But maybe two is enough in this case as well. So yeah, there's definitely a lot of interesting things to try out here. Thanks.
As a follow-up to that, how far are you away from a Schrödinger equation for ZX calculus, which is kind of related to what Robbie was asking for?
Yeah.
You mentioned Stone theorem, and Stone theorem is really a different way to write Schrödinger equation.
Yeah. I need to think about that. But yeah, being able to differentiate ZX diagrams, with a calculus, that kind of, I think, opens some possibilities and on kind of dealing with this Schrödinger's equations and just kind of solving differential equations. Yeah.
Okay.
Thanks.
Thank you. Thanks for all three teams for very nice talks. So we close the session here. We still have to clap for Richie. Everybody else. Okay, thank you, everybody. Have lunch.